Hi, I'd like to do some gas law practice with you. Lots of numbers, lots of words when you read these questions, and you're trying to really just figure out how to begin. If somebody tells you, oh, hey, this is how you do the problem, it's easy. So I'm going to help you navigate getting to that mobilization, getting that started, position of, oh, I don't even know where to begin. So we're going to look at this first problem. We have a balloon and it's 4.3 liters, 350 Kelvin, and we want to change the temperature to 250 Kelvin. These are all problems that I found in a book. So here are the steps. Number one, label. There's something amazing about you putting a variable and labeling. Rewrite what's given in that problem on your paper. From that, you're going to identify the formula. Now, what's important in labeling is writing down not only what they give you, but what they want. And so that allows you to see where you begin, what they give you, and where you're supposed to end, what they want. And from that, you can find the formula to get from where you are to where you want to be. Number three, strongly recommend solve for the unknown variable. It is so much easier to do the math if you algebraically solve for the unknown with the variables, and then you plug in the numbers. Lastly, this is the fun part. You're going to plug the numbers into the variables and do the calculation on your calculator. So it's the plug and chug. Okay, so first, let's label. All right, our initial volume is 4.3 liters. The initial temperature, T1, is 350 Kelvin. And we are going to change the temperature to 250 Kelvin. And what they want to know is what's the new volume. That's going to be our V2. All right, so I have everything labeled, and by having it all labeled, I can see this is Charles' law. We are going to use V1 over V2, excuse me, T1 equals V2 over T2. So there's Charles' law. Now, I also bring up to my mind, hey, this is directly related, so we can make a prediction. I can see that the temperature is going down, so if the temperature decreases, I'm going to predict that the volume is also going to decrease. It's going to be less than that 4.3. So let's go ahead and solve for our unknown. We want to find the final volume. So I'm going to multiply both sides by T2. Remember, if I multiply by T2, that will cancel, and whatever I do to one side, I do to the other side. So T2 is going to cancel, and we will end up with V2 equals V1 T2 divided by T1. Okay, last step, this is the fun step. We're going to take these numbers and plug them into the variables. So I'm going to plug into the V1, that was 4.3 liters. Notice I always keep those units. The units will confirm if you do it correctly. Times my T2 was 250 Kelvin divided by T1 was 350 Kelvin. Okay, let's look at the units. Kelvin will cancel and we will be left with liters, and that's exactly what we wanted. So plug this in, 4.3 times 250 divided by 350, and the answer is 3.1 liters. Now let's double check, was the prediction correct? Did the volume go down? Yep, it did. 4.3 down to 3.1. Okay, nice. So there's our first example. Let's do the second example now. So in this second example, again, a lot of words. It says we have the pressure of helium, a sample of helium, in a 1 liter container is 0.988 atm. What is the new pressure if the volume is 2 liters? So again, where I always begin is labeling. Let's see, so we have an initial volume, V1 will be 1 liter. The initial pressure, P1, is 0.988 atm. And it looks like we're going to have a final volume of 2 liters. And it says, what's the new pressure? So we are looking for P2. That's going to be our unknown. Okay, looking at these variables, I can see we're going to use Boyle's law. It will be P1 V1 equals P2 V2. And I remember that this is indirectly related. So if the pressure, excuse me, the volume is increasing, volume is going up, the pressure is going to go down. So I'm going to predict that that pressure is going to be less than 0.988. In fact, I'm going to predict that it's half. If this is doubling, volume is doubling, I'm going to predict that the pressure is going to decrease by 2, by a factor of 2. Now we're going to solve for our unknown. I want to get P2 by itself, so let's divide both sides by V2. I divide by V2 so that cancels. Whatever I do to one side, I do to the other side. So we have P2 equals P1 V1 divided by V2. And now we can plug in our numbers. So the P1, 0.988 ATM, times where I'm at V1 was 1 liter divided by V2 is 2 liters. Let's double check our units on this. Liters cancel, and woohoo, we are going to be left with our ATM. So 0.988 times 1 divided by 2, P2 is going to equal 0.494 ATM. Oh, and check it out. It halved. Yeah, it halved. 0.988 divided by 2. In AP, you will find that they'll give you problems where they just want you to be able to think it out, not even do any calculations, but go, oh, if the volume doubles, the pressure is going to half, because they're indirectly related. So that's a good one that we actually could have just done some mental math on. I also wanted to point out a reminder. This was a convenient problem. They gave us temperature in Kelvin. Just want to put in a plug, to remind you, always, 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 we have to have temperature in Kelvin. So, so, so important. Okay, let's look at this number 3. So we have another diagram. It's a piston. So this shows us that we have a volume of 30 mils, and the pressure, this is the piston right there, pushing down inside the cylinder, is 1 atm. We're at 0 degrees C. And it says if you change the temperature to 30 degrees C and the pressure to 1.2 atm, will that piston go up or down? Okay, let's go ahead and label, and then we'll start thinking, see if we can predict what we need to do. So initial conditions, we are going to have an initial pressure of 1 atm, an initial temperature of 0 degrees C, Celsius. Again, we have to have this in Kelvin. So let's go ahead and add the 273.15. That will give us 273.15 Kelvin. Our volume is 30 mils. Okay, now we're going to change all of this. We're going to change the temperature to 30 degrees C. So let's go ahead and put this into Kelvin. Plus 273.15 equals 303.15 Kelvin. And the pressure, P2, is going to be 1.2 atm. Now remember, it doesn't matter what our pressure and volume units are in if we're not using the ideal gas law. They just have to be the same from initial to final conditions. So I have ATM and ATM. That's great. And then it says, will the piston go up and down, up or down? So really, it's wanting to know volume. Are we going to have less volume, or are we going to have more volume? So V2, honestly, is my unknown. Now, I see 3 different variables here. If we just had 2 variables, then I can make a prediction. But from 3 variables, there are too many pieces moving. I can't make a prediction. And I can see, having my 3 variables of volume, pressure, and temperature, that we are going to have to use the combined gas law. So we're going to have P1 V1 over T1 equals P2 V2 over T2. Now, I want to give you another reminder on this. Coming back to these 2, if they had said, for example, here, that the pressure was constant, remember, you could use this and just say, well, pressure's constant, take the P's away, you would have had Charles' law. And here, saying that the temperature is constant, you could take out the T's because the temperature is constant, and there you have it. The Boyle's law that we had used in this one. So if you don't want to have Gay-Lussac, Boyle's, Charles' laws memorized, just memorize this one, and whatever's constant, you can take it out because it would cancel out. Okay, let's go ahead and solve for our unknown. We're going to solve for the V2. I'm going to multiply both sides by the reciprocal of T2 over P2. Notice how those will cancel. So over here, let's do the same thing. We're going to have the T2 divided by P2. So the T2, P2 cancel, and we're going to have V2 equals T2, P1, V1 divided by P2, T1. Okay, that's a pretty good size little formula there. Let's go ahead and plug in. Erase this so we have a little more room. Let's go ahead and plug in our values. So our T2 right there, 303.15K times, let's see here, our P1 was 1 ATM times our V1 was 30 mils. Notice how I'm really careful to exactly find the right unit. We have so many numbers up here. Students easily will make a mistake by plugging in the wrong value. And then our P2 right there is 1.2 ATM, always keeping and using my units. And then the T1 is the 273.15K. All right, let's look at our units. Kelvin canceled, ATM cancels, and very nice, mils. So V2 is going to end in mils, and that is the unit that we want for volume. Perfect. So, little reminder with your calculator, everything that's in the numerator you're going to multiply, and everything that's in the denominator you're going to divide. So I'm going to show you this on my calculator. We're going to have 303.15 times 1, we could leave that out, but I'll go ahead and show it to you, times 1 times 30. Now, your TIs, they're smart. You don't have to hit equals here. You can hit divide, but I'm showing you this because it's a common mistake that students make. When you divide, you have to make sure that you put that in parentheses. So divided by parenthesis 1.2 times 273.15 end parenthesis. So I wanted you to see those parentheses when you divide. The mistake that students will make is they'll hit divide and not have it in parentheses, and then they hit times, and what happens is they actually take this quotient right here and multiply the whole thing by 273. So just be careful that you have that in parentheses. I can't tell you how many times I've seen that, so I want to take the time to show you that. All right, and the answer is 27.7. 27.7 mils. So to answer the question, is that piston going to go up or down? Well, it was originally at 30 mils. Now it's going to be at 27.7 mils. It will go down. It will go down. Okay, good. So some good practice for you. Main thing, honestly, I think it sits right there. Label what you're given, label what they want, and from there, you can figure out which formula, solve for unknown, and plug and check. There are more explanations on all of these. Please watch them on Lean Think. Or if you're moving into Ideal Gas Lab, more examples for you to look at the Ideal Gas Lab. Have a wonderful day. You're terrific. Bye.